So here's the title of this lecture, Signal Processing. And in this lecture, I would like to talk about these topics for this class. First, we like to think about what is the signal and what is noise as well. And then how noisy is the signal. And there are several very simple but very useful techniques for reducing the noise from the noisy signal. I'd like to introduce two of those to you, which I think is a very general for the purpose of research. Therefore, today's topic is how can we deal with the noisy data. This is a topic, okay? And first of all, I like to see this table and figure. This is the, oops, let me move this. This is the breakdown of Nagoya city population. Here's a table that shows the actual number of the population for each area. For example, Chikusaku, where here the Nagoya University is located, has 16,000 of people. And these are numbers. In other words, these are data, okay? And you can show some statistics of this data in terms of figure like this. But this and this are also, how do I say, identical in the contents of the meaning, or is the meaning. Okay, so these lengths simply represent the number of the data, the figure here, number of population, and there's no specific meaning in order of these numbers. So Chikusaku, Higashiku, Kitaku, Nishiku, there's the only name, that's the only level of this data. Therefore, you can, interchange this data in this table. That doesn't make any change in meaning of these statistics. So this is the data. This is the samples. This is a set of numbers which is associated with the real world. Okay. So my point is that there are another type of data that is indexed by some physical parameters like space, like time. For example, this is the growth of Nagoya city population from 1098 up to the last year. So these are also representation of numbers, data. But you can see, very simply that the number of the population of Nagoya city is growing and saturating recently. So those meaning is brought by indexing these data, numbers, okay? So if you, for example, swap these two numbers, you lose completely the correct meaning of this data, okay? So I call these sequential data a signal. Of course, there are a lot of definitions of signal you can define in many ways. But my definition of signal is sequential data or indexed data. And index is not always one-dimensional. You can use two-dimensional indexes. For example, image is two-dimensional. It has two-dimensional indices, x, y. If you swap any of them, then the image itself will be destroyed. Okay? So index data is a signal. That's my definition. Then from this data or signal, you can somehow understand what does this mean. For example, the ref population of Nagoya city would be something like 2.2 million. That was achieved by at 2006. And also growing speed is somehow reducing, but still we are growing in number. And also, we see a very interesting phenomenon here. Here's a dip, 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 dip. Still, it's growing now, but you have a periodical dip at every April. This is very reasonable because people move in Japan, typically during the spring season, March, April, May. So here's mean that people going out, and then people will come back and increasing, but still going out. And such a movement of people can be clearly shown in this signal. Okay, so analyzing these, or understanding these properties of data in terms of the index data is the analysis of a signal. That is the important definition and understanding of what is data and what can we do with data. So again, I say data is a simple number or set of numbers, but a signal has a very important property that is indexed by a variable. In most cases in this lecture, this independent variable n stands for the time, progress, but it can also be a measurement of the space or any other physical meanings. Okay, so again, signal is a set of data which are ordered by index. That is the definition of signal. Therefore, we write like this. The variable x is indexed by variable n, and variable n changes from 0, for example, to n minus 1, which means that there are n samples, and that order is meaningful. You cannot swap the order. So please be familiar with this representation. Okay, again, the Nagoya population, I zoom in up in a particular, years of the data. And from this figure, we like to think about what is noise to the data or to the signal. Okay, so as I shortly mentioned that from this figure, I think you will be realize that, for example, the average of the, or rough estimate of the population is like this, average. And also, we see the growing of the population trend. This is a kind of a trend. And also, more importantly, we see a periodical fluctuation like this. Maybe you say periodical fluctuation. If I spell it wrong, please correct. Or you can find the correct spelling in your handout. But anyway, what do we see in the blue line is the superposition of these three different signals. Each of them has different meaning. For example, this periodical fluctuation clearly means that 1 year is a period of social activities. Things like that. So if you denote the total number of the population with the sequence index of n, then Pn would be, understood that the sum of average and trend if you write it as Tn, and also periodical fluctuation if you write that Fn, for example. So there's 3 signals composing this signal. And if you are interested in the people social activities during 1 year period, then you like to focus on the F, periodical activities of human, which means that other signals are noise to your research or analysis. If you are interested in the global trend of, for example, warming of the Earth and how the population is related to that, it is also, in that case, you may be interested in thinking about trend rather than fluctuations or average. So it depends on what you like to do. Well, it depends on what kind of meaning do you like to extract from this signal. Okay? So what I'm going to talk about, denoising or reducing the noise, is that I like you to give or to understand several ideas or methods to focusing on particular meaning of data or real-world data by means of denoising or noise reduction methods. Okay, so this is introductory part. And let me go back. So this is one mathematical representation that I mentioned of the ideas that I mentioned. The average actually is not depends on the time sequence, therefore average is constant. And for example, trend, if it is linear, which means that it can be written in a line, then that would be something like this if you write as a mathematics. And periodicity has been represented by a sinusoidal signal like this. So periodical part can be, or hopefully be written like this. And the other one, this must be error, which is not be described these 3 ideas. So rewriting the signal in terms of mathematical representation, this is a great idea. If you have an index here, then you can rewrite signal in a very specific manner. I guess you studied about the statistics. There are average, there are the confidential interval, there's a estimation, there's a hypothesis verification. Those kind of things has not associated with the kind of physical, how do I say, world in some sense. But this is very, very related to the physical world because n is time, clearly time. So you can understand the shape of the data signal in terms of the, time function. That's very nice too, particularly for engineering field people. But again, I'd say that n is not need to be your time you can use. This is the number of the gene order or whatever, spatial locations, whatever it is. Okay? So how can we, estimate those signals? Probably you can guess how do you calculate these different meanings from the signal. Average is very simple. You can just add all samples over the time, all time, which gives you that. In this case, n is very long, maybe 10 years, 20 years. Trend, if you like to see the trend, you need to at least disregard these small changes And it can be done by averaging the certain lengths of the data. And the averaging period might be better, for example, 1 year. So if you like write this 2m plus 1 in some reason, by some reason, then you can estimate the trend here by like this, 2m plus 1 over 1 times, let's say m is equal minus large m to large m, but p is centered at n, but shifted from small m. This is the local average around this. So this point, forwarding m point, backward minus m point, and you average this, then you can get somehow value which is not affected by the periodical kind of things. And if you can, estimate those kinds of things, then you can simply subtract this. This is average, so I call this Pn minus C minus Tn will be equal somehow, fluctuation, hope-free. So you can calculate from data. It's very simple. So I like you to understand the powerful, tool of mathematics when you understand the phenomena in a real world. So actually, I wrote a very small, simple code in MATLAB and run that code in order to get the average, trend, and periodical fluctuation, which gives me like this kind of things is easily extracted from the real signal by a couple of lines of code. Okay. Then you may think that noise reduction is very, very simple because we highlighted that very simple nature that the observed signal is sum of the signal that you like to use and other signal that you don't like to use. This is sum. By the way, this is not all general case. There are a lot of classes of noises. And this is very most common case, which is called additive noise. So in this case, we call the D is additive noise, and the other noise is convolutive noise. Convolutive noise is another class of noise. If you knew the word convolution, then you may understand what does it mean. But this is not always the case, but this is a very simple and useful case, additive noise. So suppose that the noise is additive to the target signal. Then if you like to concentrate on the target signal, you may just subtract the noise from the observed signal, noisy signal. Just simple subtraction. This is one of the most fundamental mathematical operations that you study in the elementary school, subtraction. You don't need to use a huge computer, but just subtraction is very easy. So essentially, basically, or principally, noise reduction is very simple operation. But of course, you do not have any idea about what is noise is. All you have, the information all you have as a sequence of number is this, observed signal. So, imagine that you are given the number 6 and you are asked that, guess what is the elemental numbers that makes sum to the 6. You can answer 1 and 5, or 2 and 4, or 3 and 3. There are, you cannot determine. Only knowing that the adding result is 6, or summation is 6. So the difficulty of the noise reduction is that fact that you do not have any information about noise. So if you knew noise, then it would be probably simple. Do you agree, Tukun? Okay. Okay, so then I'd like to briefly mention about the measure to evaluate how the signal is noisy. So there's a very uncommon measure among the engineers, SNR, signal to noise ratio. Let's review what is the definition of SNR. SNR is the ratio between the power of the noise signal and the power of the target signal. Power of the noise signal and the power of the target signal. This represents the power. Power is the word that is familiar to electrical engineering world, but not familiar to the social scientists and other field people. So let me denote in different way. The power here is calculated by this. I have n sample again, then the power is given by this. Is equal to 0 to n minus 1 S n square. It's a very simple definition. You have numbers and you square, you take square of that and sum it. Then you got the power, okay? Or maybe you can, okay. Then in the same way, you can calculate the power of the noise completely the same way. But the signal is D here. Then you may be better to be familiar with this symbol, decibel. Decibel would be some funny name of the unit, but decibel is the unit for ratio, like this. And this is defined like this: 10 times log of 10 PM over PS. His value, gives you SNL as a decibel. For example, if the noise power and signal power is equivalent, then of course this value becomes 0 because log of 1 is 0. If the signal power is very sufficient than the noise, like for example 1000, then this value becomes 30 decibel. And if the noise is bigger than the signal, this sometimes happens, unfortunately. Then the SNR is minus 10 dB. So SNR is a very useful measure to cope with a very wide range of the value because it uses a log for converting the big value to the manageable values. Okay, so here's the noise and the definitions, and this is the calculation method. And again, we need to know what is noise if you like to reduce or eliminate the noise from the target signal, from the observation signal. And actually, unfortunately, it is not always the case, or a very rare case. But we have, for example, a known signal like PSN, power supply noise. If you are working in a experimental engineering field, you come up with, power supply noise in some, measurement, I guess, because the power supply is a very big power. Therefore, that leakage will be, popping up in a various naive measurement. So this is one typical result of a student's lab measuring something. Here, the shaggy signal is actually the observation. Yes, target signal, S, target. But it is contaminated by a very big power signal. This is a power supply noise. Therefore, it is sinusoidal wave which has 60 Hertz, which is the power frequency here in Japan, in Nagoya. Is that. So this is a sinusoidal signal which has a 60 Hertz frequency. So do anyone know how can you write the 60 Hertz sinusoidal signal in a mathematical representation in a discrete time? Probably students from engineering school are a bit familiar with that kind of things. But let us review about the discrete time sinusoidal signal. This is very useful again. So again, sinusoidal signal has its background circular movement like this. You start from here, for example, and step. Every step you go move on a circle, having or keeping the same difference angle from here to there, 1, 1, 1. So every time step 1, you go here and there. And if the angle or relative angle between two samples are very big, then you go very fast. And if the angle is very small, then you go very slow. Therefore, this actual signal has several properties, but the most important characteristics of signal is its interval or period, because it represents how fast do you go around. If the period excuse me, is very long, then you go very slow, and the period is very small, then you fast. So suppose that you write the symbol n. Again, actually, this is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then, which means that you subdivide or divide whole circle into 12 points. 1, 2, 3, 4, 5, 6, 7, and 9. And if you have knowledge about cosine or sine, then you can easily imagine that you can know the place of the let's say you can know the cosine value at the particular time point of the circular point location will be represented by this sinusoidal signal. So in general, we can write sinusoidal signal like this: A times cosine omega 0 n plus phi. This is the general representation of discrete time sinusoidal signal. And of course, A is amplitude. Amplitude, which is the height of the signal. And omega 0 is the angular frequency or normalized angular frequency. Angular frequency. And this is calculated by this 2 pi over n, because you need 2 pi. You need n samples in order to complete the circle, which internal angle is 2 pi. And then phi is very important. This is the initial phase. This specifies where do you start to turning around here. And therefore, omega 0 is calculated by n over 2 pi, and things like this. Okay, so this is a general representation of discrete time sequence. Okay, then let's see. We are discussing about the power supply noise, which has a 60 hertz as the fundamental frequency. And that is actually a signal in the physical world and continuous time. So we need to convert that continuous time representation to the discrete time representation. In other words, from t to n. And 60 hertz, which means that the period of sinusoidal signal is 1 over 60. Okay, therefore the period is 1 over 60. And if the discrete signal system is sampled at 1,000 samples at a second, which means that 1 kilohertz is the sampling rate, then these lengths in time can be converted the lengths in sample numbers by simply multiplying by this number 1,000. This is the sample period. M. And as I mentioned, the normalized angular frequency omega 0 can be calculated by n 2 pi over n, which is like 2 pi over n, which is like 1,000 over 60 times 2 pi. Am I correct? Yeah, then it is like 6 pi? No, maybe. Therefore, was 50 over. So if I develop wrong equations, please, let me know. I always do that. So if you can calculate the normalized angular frequency, then you can specify the power supply noise in terms of mathematical representation, which is 50 over 3 pi times n plus phi. Okay. So we can develop the noise signal in terms of function of n. Okay. So once we know the characteristics of the noise, we may be able to subtract that from the observation signal. Again here. So we knew that this signal can be written by a simple sinusoidal equation, terms 50 over 3 pi n plus phi a. Okay. But how can we? Because there are still undetermined variables, a and phi. Without knowing this, we cannot build estimated noise. For example, if you estimate a like this, very big waveform, or if you estimate phi like this, just opposite direction of the polarity from here. Of course, you can shift in order to adjust these function to best fit to this noisy signal on this graph. Mathematically, it is not easy to find the optimal location and height of the signal. I have an example. What happens if you use the wrong estimate of A and wrong estimate of phi when you subtract this signal from the noisy signal? Okay, this is an example. If you subtract exactly same signal from this and this, then what you will obtain is complete zero. Of course, this is a very simple mathematics. But if you try to subtract from here one sample delayed version of this, which means that you lost in accurate estimation of the phase, then the result is like this. You almost have a power signal that has 0.3, 0.4 amplitude here. And the worst case actually is that when you fail in estimating the phase and you use the phase different in 8 point from the original signal, then actually noise is doubled because the superposition of the noise will work to enhance the noise signal. Therefore, the noise value becomes 2 rather than 1, which is the original signal. So estimating the phase and amplitude is very, very, very important. Actually, it is not easy or difficult. So I like to highlight that fact that the simple signal subtraction is not easy, not always easy, due to the lack of knowledge about the noise. So if you knew 100% knowledge on the noise, then it would be easy. But if you don't know, then even if you knew about the frequency of that signal, it is not easy. So what else is the approach to eliminate those signals, the characteristics of which is somehow known to us? The one simplest way is to eliminate all signals that has the certain frequency, which is lower than predetermined frequency. For example, in this case, you can filter out all signals that has the fundamental frequency less than 100 Hertz. Because power supply noise has 60 Hertz at the fundamental period or frequency. Therefore, if you eliminate all signals from the observation signal, which has the frequency lower than 100 Hertz. In other words, you may know the word high-pass filtering. High-pass filtering. High-pass filtering is a filtering to do something like this. If you have a frequency f, and if you have a signal s, and it is a function of f, then you eliminate all lower frequency component except for the frequency signal which has higher than certain frequency f0. So by doing this kind of operation that eliminate the lower component from the whole signal, then you may somehow reduce the power supply noise, definitely. Of course, this destroys, unfortunately, the target signal as well. Suppose that if your signal, which is your interest, has also the frequency component lower than 100 Hertz, then that part of your signal or your target signal will be eliminated. Therefore, your target signal would not be rebuilt completely. But even that, think about SNR. If the SNR of this part is very, very bad, then if you disregarding this part would, in total increase the SNR of the, processed signal. Okay. So at this moment, I need to briefly mention about the frequency of the signal, which is not familiar to all of you. Like you, maybe, I don't know. So frequency, signal, Fourier. Do you know the word Fourier analysis? You know? Oh, great, 素晴らしい. So I need to little bit talk about Fourier analysis, which most of you, for most of you, this would be a sort of review, and simplest review. But let me say that a signal xn, which is indexed by n. Sorry, I started sometimes from 0, sometimes from 1, but please do not mind. That's not so big difference. Is given by a weighted sum of n sinusoidal signals. So if you have limited length of signal, then you have the counterpart of sinusoidal signals. By summing them, you can completely rebuild the original signal, which is written in mathematical formula like this. You add up, sum up. Let me E cosine n over 2 pi k times n plus phi. Actually, this is a function of k, and also amplitude is very close k. So this is the inverse Fourier transform, which means that if you knew the amplitude and the phase for every k, k is a multiplication of fundamental angular frequency. In our case, 50 over 3 pi, 6 pi. Maybe I calculated wrongly, but maybe 50 over 6 pi. It's like that. So if you understand, or if you accept this fact as a mathematical fact, then you will be soon know that if you start, or if you disregard some component which associate with particular case, which gives you a lower frequency than 100 Hertz, then you can eliminate all signal component which has a lower frequency. So let's calculate what k would be used and what k would not be used. And again, n over 2 pi k is the normalized frequency. And this is independent from actually the sampling period. If you sampled the signal at 1,000 Hertz, by the way, we usually write Fs, use Fs as a sampling rate. Then a real frequency would be like this, n over Fs times k. That is the corresponding frequency f, okay? And so we may write f0 here. And if the f is less than 1,000, it would be fine. 100, it would be fine. That is our, our restriction. use the lower frequency component only. And this is easy to calculate k. So k should be less than, suppose that n is 256, for example, and 100 is divided by 1000. This is the sampling frequency, which is like 25, this is 25.6. Therefore, if you use the signal component, if you do not use the signal component less than 25 k, in the case 25, then you can totally disregard the lower frequency component. This can be also graphically represented by the same, essentially same figure that I wrote in the last slide. Again, we have a small, we have a 0 value of amplitude and less than k0, which is 25. So if you start from 26, then it's fine. It is, in other words, in a frequency domain, which is represented by k. You do the lower part of the AK, or at the smaller k part, less than 25. You can eliminate the noise and other signals, which is harmful to the real observation. So mathematics itself is very simple, but the idea is not probably simple, or intuitive at least. Intuitive, at least. Okay. So this is the discrete Fourier transform. At least by knowing this fact, it is sufficient to develop this class discussion. So I forgot to bring my Coca-Cola, Diet Coke. So that was bad of me. But anyway, I don't mind if you drink or maybe eat. I don't mind. As usual class, you can relax and feel at home maybe. Okay, this is the equation for the discrete Fourier transform. And high-pass filtering will be executed that by using the only k, which is above 25 in this case. And in fact, Fourier transform by computational signal PC or laptops, it's very, very, very easy, very, very cheap now. So you can do this and reconstruct the noiseless signal by utilizing the inverse Fourier transform and Fourier transform. It is okay. But still, there are a lot of easy ways. One of that is to use the linear filtering. So linear filtering is a very useful topic in signal processing. Actually, it is one of the fundamental part of the signal processing applications. But I'm afraid that we do not have time to go through that idea. So I just like to mention about very, very, very simple realization of high-pass or low-pass filtering using the linear filtering idea. Okay, this is just idea. Therefore, the explanation would be a very, very intuitive, but maybe you can get know about the idea. Okay, linear filtering is the very simple system which has input and output, and some elements that gonna branch the signal flow into different direction, and you can build a delay, and you can add the signal some knob, and also can amplify the signal by this unit. Fine. Okay? So here's the input, here's an output, and signal goes through this and like this. Therefore, here you summing up the sample and one sample delayed sample, which can be given in mathematical method way, 2/1. This corresponds to 0.5 xn plus xn minus 1. Okay. This is very simple linear filter. Another one is also very simple. It is like this. It's also branching the signal here and go through the delay element. And you here calculate the difference, which gives you xn minus xn minus 1. This is another linear filter. Okay. Suppose that two different linear filters. The functions are, difference are very, very small. This is summing up. This is the subtracting out. But the performance is completely different. Let's see, let's imagine what happened if these two signals are given to this system. Okay, this is a low frequency signal, which has a longer period in time. Okay, and the bottom one is the high frequency signal, which is a short period. And if you sample this signal into for the discretization, then you got these poles and burrs and things like this. Also here you got things like this. When you sample that two signals at the same sampling frequency, the signals looks like this. Okay. In this signal, the values or height at the two consecutive time points, n and n minus 1, they're very close, similar. There's very little difference between two. In this signal, on the other hand, sometimes the difference is very big, or even the polarity is flipped. Here's a plus, here's minus, plus, minus, things like that. So imagine that you add two consecutive samples for the low frequency signal. The results are almost the same because these two numbers are very similar. Therefore, the average also are very similar to these numbers. But in this signal case, for example, here you got a positive and negative values in a consecutive two samples, and you adding up them, then it would be disappeared, right? Because plus and minus would be canceled out. Therefore, this linear system works as low pass filtering would be eliminating the high frequency component. Okay, so simple averaging is very beneficial for the lower frequency signal, but if you have the higher frequency component, those components will be decreased or reduced in signal. Let's see different one. Here, completely different thing will happen because this and this are very similar. Therefore, if subtract this from this or this from this, the difference is very small. Difference are very small among these two values, although difference from this and this and this are big. So for this linear system, well, by this linear system, you can somehow, attenuate, reduce this signal. But this signal will not be so much affected by the simple subtraction neighboring signal. So I hope you see some idea about how a linear system will work as a frequency selector or frequency, a filter to the different signal component in different frequency. But this is a very, very, very simple idea. You can optimize the frequency characteristics by using a lot of delays combination combined with a lot of weights. Particularly if you introduce the feedback loop into the system, you can get a very sharp frequency characteristics to the system. But anyway, I hope you understand also the frequency, linear filtering gives you filtering out or attenuating the lower frequency component, and then it will work as a noise eliminator. So I guess the exercise of this lecture will be related to this. No? Something? Okay. Okay, so these are the stories that we somehow know about the noise characteristics. In our case, it is that the noise is composed of 60 Hertz sinusoidal signal. The next challenge, again, so I skip this. The next challenge is the case that the noise is random. Random signal cannot be written by a simple math like cosine something or log something. Random is random. You cannot know what x is without observation. So random variable is a kind of symbol, just symbol. This is not a number. But we cannot determine the value of the random variable always, but we can determine the distribution of the data. Distribution of the random variable. What does distribution mean? The distribution means that how likely the random variable takes the given value. For example, in the case of dice, you have 1, 2, 3, 4, 5, 6. And the distribution of dice is written like this. P, I use large P, subscripted by X. This is a random variable name. And, with K. K is a number that associates with the realization of random variable. And this represents the probability that the random variable x takes the value of k. Okay? So if the x is the die, then px3, for example, is of course 6 solvable. And for whatever k, from 1 to 6, the probability is equal 6 over 1. Okay? 1/6. And if you read that, okay, maybe, if you think about dice, this always holds. This is a true. And number 6 is also true. You can determine this. But you cannot determine what will be the next die. That is random. Okay? Even the phenomena is random, but you can define the characteristics of the random phenomena. That's a distribution. And associated with distribution, you can also determine the expected value. which is given or written by this expectation of x, the dice. Even you do not know what is the x, but you can calculate this by summing up all k's from 1 to 6, k times pxk. Okay? This is the probability that the die is k, and the number of the k is here. And because you know this completely for one dice, then this can be easily calculated. This will be 1/6 times 1 plus 2 plus blah, 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 6 would be 6/21. This is also true. Whatever you die, fine or bring. This is not known, but the expectation value can be determined. That's a secret of the gambling. It's always, better for the, providers, not players. Okay. And you can calculate, of course, another expected statistics. Not only x value itself, but for example, the sum of 3 dice is 3 times 6/21 is equal to 2/21. So you cannot bet more than this if you go to casino, and they has a very complex funny rule, but you can calculate the expectation number, and you can do better bet if you find the whole of the rule. Sometimes a very clever student, MIT, Stanford, find a very funny, whole of the blackjack tables rule. That is usually local to each table, and calculate the probabilities for the all possibilities, and find that by this strategy, they always, they can win as far as they continue, because this value is easily calculated from the fact that the shuffling randomness is determined by the distribution or things like that. Okay, so here's a secret of random variables. Even you do not know the actual number, you can calculate a lot of things associated with the random number. Then what happened? Random process. So random process is the extension of the random number to the time sequence or signal. Okay. It is that same as I mentioned earlier of this class. Random process xn is a set of random variables indexed by n. So far we have assumed that x is the data, therefore xn can be observable. But now we do think that xn is a random variable. Therefore, we cannot, observe that value. But we can observe one realization of xn for every observation. Okay, so again, we can do the same notation for this pxxn x for the continuous case. So I'm sorry. This is a little bit complex. Continuous case. Actually, it is better to use f rather than p, because this is a probability function, not a weight math function. Fxn n gives you a probability that the sample observation xn is less than or equal to n. Okay? So this is the definition of the probability distribution of random variables. See that here's an n. So this probability changes for every n. Therefore, if the time is growing, then the probability distribution will be changing in general. And it is easy to think that the stationary process, which means that Fn, not Fn. I think I will come back at this in the next class, which I'm going to try to talk about more. How do I say? More about time domain analysis, but here like you mentioned that when the process is stationary, then you can say that this is independent from time index, and also when the process is stationary, this is not independent. The variance of the signal is also independent from the order of the observation. So stationary process is very important assumption and idea to make the system more simple. So keep this in your mind. Let's see the different signal. Okay, this is a signal. Next, I like to talk about. Here's again observation. Observation is xn, and behind that observation, you have a target signal and noise signal. But in this case, noise signal is random. So here in this figure, this smoothly changing signal is S, and this is deterministic. Therefore, you can write this in a mathematical formula like a superposition of sinusoidal signals. On the other hand, these shaggy parts are given from Dn. This is a random signal. So again, if you add the random part to a deterministic signal, you get also random variable. So the observation itself, for this signal, in mathematical meaning, observation signal is also random signal, okay? Because the random component is added. And from this figure, I like you to notice that the SNL of the signal is like 12 dB, actually. So this is a typical length of the wave height. Wave height, that corresponds to the actually root of signal power. And also here, this height is corresponds to a root of noise power. And you see the ratio between this and this, or square of this and this, is 1 times 4, or 1 versus 4. Therefore, I say roughly SNR of the signal is 4, which is the 12 dB. No, 6 dB, 12 dB. It's a rough estimate of the SNR is 12 dB. Okay, so here's a target signal. So far, I know I'm going to talk about. So because we are based on the assumption that the noise is stationary, and we also like to assume that the noise is zero, mean. The average of noise is 0, independent from n. So each noise sample has 0 as a expected values. And because S, we assume that S is a deterministic signal. Therefore, expectation value of Sn is not meaningful. It is just Sn because we can determine Sn in terms of n. So if you calculate the average or expectation of Xn, or a random variable of Xn, it is sufficient to calculate the expectation value of dn, because the Xn is the sum of Sn and dn, and Sn is deterministic. Therefore, you can write this. And this, because it's 0, this value actually is the Sn, real value, target value. Whenever the signal is random and 0 mean and stationary, then the expectation value of a random variable Xn is the true signal. This is a, how do I say, very good nature of the random signal. But you may guess that, is this always hold? Does the random signal always have 0 mean? It is not true, actually. We have a lot of signals which has non-zero average value or as a random noise. But I can give you a very, very simple, good idea. This is very, very useful, so please remember this. That is the secret. How can we make noise to be a 0 mean? Okay, we are discussing about Xn, that is equal Sn plus Dn. Whatever Dn is, we calculate the average of Xn by some means. I don't know how to calculate this. Actually, this is not easy sometimes, but it is easy in many cases. That represents that Sn bar plus Dn bar, okay? And then subtract this from the original signal. Xn minus Xn bar is equal to Sn minus Sn bar plus Dn minus Dn bar. Okay, bar means average. Oh. Okay, then see or rename this like S0 n. Rename this D0 n, and rename this X0 n. The same equation hold here, and you may know that you may see that the average of D0 is 0 because the average of D0 is the average of Dn minus the average of Dn. It's clearly 0. So it is always very, very good idea if you like to analyze the signal in terms of the changing the time, or to take average subtracting from the original value and make the signal to be a 0 mean. That makes you a very, very, how do I say, feasible characteristics. That gives you a feasible characteristics of the 0 mean signal. Like, for example, this here. And this is very, very good because if this holds, then just simply estimating the expectation value of random signal can realize the noise reduction. So how do we implement this expectation? That is the issue, okay? So what is the most common way to calculate the expectation value of a random variable? taking. Okay, it's very, very simple. Sorry, my question makes you a little bit puzzled, but suppose that there are 3 red balls and white ball, 2 white balls. You don't know the ratio between red and white. That is a random variable. What do? You try, maybe 100 times. Then you got something like 60 versus 40, 60 red, 40 white. Okay, this would be a sleep time too. That is a very, very practical way to calculate the estimation. In other words, multiple observation of the phenomena is very, very efficient and useful. So do the measurement again and again for the same situation. And if the noise that you have a headache with is random, then you eliminate them by the multiple observation. For example, these are 2 different observations of same random variable xn. For example, if the n is, for example, 132, that is here, and here, the values are different because it is random, but the random component is positive here and negative here. Therefore, summing up all those things would make you easy, because the noise plot becoming small and small if the noise is zero mean. So this is very useful. So please be patient about observing the real world. Not rely on a single observation, but do that repeatedly. For example, in acoustic case, we sometimes, we used to measure the room acoustics, but that is very, very fragile. Therefore, students try to measure 30 times, 40 times, and do this superposition. That gives you a better SNR signal because the noise is random and zero mean, okay? So please remember this. Multiple observation is very, very efficient. And the same idea can be utilized for the single observation, but the target signal is periodical. If you know that signal is periodic, then you can do something like this. You pick up this part, and you pick up the same period, and you pick up the same period, and do the same thing. Add them together. Then the noise component here and here are completely independent from each other. Therefore, the adding them would be, noise-free. So here's also a very efficient way. But don't forget to try to do multiple observation. And other way, that is a way that I don't recommend you much. But sometimes lazy people do this. Local smoothing or local averaging. I don't know. I don't go in detail about this, but almost the same thing can be done by local averaging. The idea of local averaging is like this. You have samples, and that is contaminated with noise, and you like to trace this smooth line. In order to eliminate the noise component, you can also use these samples as a multiple signal source by adding 1, 2, 3, 4, 5 samples and calculate the average value as an estimate of the value here. Probably the average value is somewhere around maybe here because this is extraordinary value. Therefore, the This gives you a very biased average here. But that is better than use this signal value. And this is the local averaging. And a little bit smart way is to calculate the median of the signals. There's a 1, 2, 3, 4, 5 samples, and average is here, but median, central value of 5 sample is here, this. Okay. So this is the median. And this would be an average. Median filter is good comparing it to the average, because when you calculate the average, it's destroyed the signal characteristics of the SN as well, because SN samples are also taken into account in the averaging. Therefore, the signals get smoother than the original form. But the median filtering doesn't average out. Therefore, that is somehow robust to the noise. But in order to calculate the median, you need apply some sort, local sort. Sort is sort. SOR. You need to sort the sequence. That is somehow headache. If the locality is very long, average is very easy. Okay. Sorry, I went very quick for the last part. And this is a result. Excuse me. This is a result of the 3 methods. Median filtering. If you increase the area of the median calculation, the signal gets smoother and it gets closer to the original signal. So it looks that in the best case is obtained by a very long period of a smoother, average local samples. But for the average smoother, if you apply a very long window for averaging, in this case 9 point, it looks pretty much smoother than due to the nature of the averaging of the SN itself. Therefore, somehow result is not good as the result of median filter. Again, this is a 3-point result, and this is a 5-point result, and this is a 9-point result. So it's up to the situation. So you need to carefully choose what is the best window. And I didn't use the word comb filter, but actually these kind of things based on the simple single observation and checking out the periodic signals and summing up them is called comb filter. And the comb filter result is like this. It's not so much good at median filter in this case, but I don't know. It also depends on the situation about that. But anyway, in all cases, we got a far much better result than the original waveform like this. It would be 12 dB or something, and I guess this is more than 20 dB or more. So all these algorithms are very, very simple and easy. So it's good for you to remember these ideas for the real applications. Okay. So here's a summary of today's class. I defined that the signal is a sequence of data. That is very important. Not limited to the time sequence, but you can also think about the space sequence and 2D sequences and also. And additive noise we talk about additive noise only. But additive noise is mathematically very, very simple. And if you know the noise, then it is feasible. But you don't know that. That is the reality. And signal to noise ratio, oops, I'm sorry. I skip. Signal to noise ratio in decibel is the classical standard manner of evaluating the noisiness of the signal in engineering field. And frequency filtering out the certain range of frequency signal is very effective. If the noise is well known, like deterministic noise, power supply noise, and local averaging or multiple observation, those kind of things are very efficient for the random noise. And actually, there are a lot of more state-of-the-art denoising methods or researches. But most of them depend on the target. For example, in our case, speech or music. But in other applications, that would be not like that. So you need to study about the particular method about that. But all those things that I told today is very generic. So you can apply somehow this method to your program. Okay, so if you have any questions, I'm happy to answer if I can. No question? Good. So let's see next week. Thank you.